Hello and welcome to E233. I'm your instructor, Gregory Myers. This video, we're going to take another look at an older version of our P4, specifically the one that focuses on the physics demo. As a matter of fact, some of the content in this video will overlap with what is in the physics demo. And particularly what we're going to take a look at in this video is going to be building some of the functions. Now I'm going to work through the Projectile 1D version 3. If anything, we want to talk a little bit about the difference between our Projectile 1D version 3 and the earlier version 2 that was found in our P3. Now, it's not essential that you have completed the earlier version of the P3. However, it is important that you understand the concepts outlined in this video. And particularly what we want to do is we want to focus on the fact that we are passing variables not only by value, as in the case of our y init, but also what we're doing is we're passing the address of the variables so they may be updated inside the function, and particularly our t final, our y final, and our vy final. One thing that you want to keep in mind as we're going through this one is that the responsibility of where we are going to display the results will have changed between our P3 and our P4. If you're uncomfortable with this concept, I encourage you to go back and take a look at the setup videos for both our P4 and our P3. So to begin with, let's go ahead and take a look at the Projectile 1D version 3. And we'll go ahead and navigate to it. And let's talk a little bit about the input arguments. We're going to spend the majority of our time on this function, and then I'm going to leave the other ones for you to finish. In other words, what we want to do is we want to take a look at not only the values that are being passed, but the data type associated with them. And so let's go ahead and update our function comments. I like to simply go ahead and provide the entire function signature up here under the name. Perfectly fine if you only want to include just the function name, and the description of the function is we are calculating 1D motion using a combination of by-val and by-ref variables. Once again, I'll use that sort of interchangeably. In this case, what we're doing is we are either passing a variable by value or the address of a variable. And so that gets us now to our argument list, in that we have our y init, which is going to be the initial height. And we also want to take a second to mention the data type for it and emphasize that this is by val. In other words, a copy of it is made to the function. And then taking a look at the other ones, we have our double for our t final. But notice now this is the address of the t final variable, which allows us now to update it inside the function. And we are also going to refer to that as essentially by reference, which is, once again, a topic that you'll pick up on in later programming languages and frameworks. We also have our y final, which is the address of the y final variable. Also by reference. We'll have our double now for our vy final, which is the address of the vy final variable, also by reference. In other words, those are going to be the three values that we intend to update inside the function. And then lastly, we also want to mention the return value and emphasize that that is in fact different than the three variables that we wish to update inside the function. This is the one that is on the left side of the function name in the function signature, and that is going to be an int, and that is just simply going to reflect the success or failure of our function. At this point now, I would encourage you to go back and take a look at the PowerPoint that I provided for you regarding the 1D motion and later on the 2D and the beam equations. And what we'll do now is we'll simply go through and we'll set this one up, or work through how we would go about setting this one up as compared to its P3 equivalent. And so the first thing that we want to do is we want to have some sort of variable that can track our results. And for right now, we're going to be very optimistic. We're going to have minimal error checking this one. We're just going to say results are equal to exit success, and then return our results. Truthfully, this variable is not very effective in this particular example. We're being very optimistic here. We're only going to do some very minimal error checking, if any, at these earlier versions of these functions, but it's just to get into a good habit of having this variable. Now, at this point, then what we want to do is we want to go through and create or declare rather those variables that we know that we're also going to need here. Particularly what we want to have is the variables that are not already in our function signature. So in other words, normally we would have had to have declared a tFinal variable, but if you'll notice that we are being provided the address of the tFinal variable, we also would need to declare a yFinal variable. We do not need to do that because we're once again provided it in the function signature and the vyFinal. So that leaves us with just a few additional variables that we need to declare, and specifically our tinit and our vyinit. And the other ones, we are going to either leverage the function signature for, or that we will discover that we in fact do not need them. But let's go ahead and initialize these. Our tinit is going to be equal to 0, and our vyinit is going to be equal to 0. Now, at this point, what we want to do is we want to calculate the values that we wish to update. And I'm being very careful not to use the word return, because the only thing we're going to return is going to be results, either exit success or exit failure. All right, at this point, we will once again use our equation for tFinal. And our tFinal is going to be equal to the square root of -2 times our yinit. And we are going to divide that by our AY. Now, in the earlier P3, our AY was a constant that we needed to define up top, which we will once again do. And we will define it as -32.2. But you'll also notice that we're getting, specifically, if we go ahead and build this, you'll see that we are going to get a warning on the line for our tFinal. And it's specifically saying incompatible types when assigning to type double from type double. And essentially what it's doing, arguably a very poor job of saying, is that you have passed the address of tFinal, but you are trying to update the address and not the value at that location. And so to accomplish this, use the indirection operator. And that is fundamentally then the only change in the equation from our P3. At this point, we can do the same thing now with our yFinal and our vyFinal. And so we'll go ahead and calculate our vyFinal. Once again, remember to use the indirection operator in front of it because we are leveraging the address of our vyFinal. And that is just simply going to be our vyinit plus a_y times our tFinal. And once again, if we were to compile this, you'll notice that I'm going to get an error. And I need to remember to use the indirection operator for our tFinal, because once again, we're passing the address. And if it helps you a little bit to use an extra set of parentheses, that's perfectly fine. Basically, we want the value at our tFinal variable, or at the address of tFinal. We want the value at the address of tFinal. And lastly, we want to do the same thing now with our yFinal. Our yFinal is just simply going to be equal to our yinit which we need to go back up and declare, or just simply hard code as 0. Once again, that's just for further expansion later on. We want to use the indirection operator for our VY, or rather not for our VY init, because our VY init is locally declared. And then we do once again want to use that though for our T final. And once again, these extra set of parentheses are just for us if we need to understand the difference between the multiplication operator and the indirection operator. And then simply add the third term of 0.5 times our constant acceleration times, in this case, the power function of, once again, our T final squared. Basically, everywhere I have passed the address of one of the variables, I need to remember that inside the function, we need to use the indirection operator. At this point, then let's go ahead and build it one more time, make sure that we don't have any typos. And we do want to go ahead and declare a VY init and initialize it. And our Y init is passed as an argument to the function. And so we should be set to go now. The main difference that we're going to do in our P4 as opposed to our P3 is we are not going to print out any of the values. We are going to shift that responsibility now to the calling function. In this case, we intend to call this from our main. So let's go back up to our main. And hopefully you have correctly triaged your switches at this point. And what we'll do is we will push what would otherwise have been handled inside of the function out to the main, including the declaration of some of the variables that we're going to need to complete our table for our P4 sample. You'll notice a couple of things here that I have emphasized a particular format spec, in this case 8.4. That will change depending on the project, so you want to make sure and get an update version of the samples file. But also you'll notice that we want to continue with the pattern of having our Y final, or T init, T final, and so on. So we've got a couple of options here. We can declare some additional variables up top, or we can hard code some of these values. Either is perfectly fine, but at the very least, we need a way to capture our Y init. So what we'll do here is we'll go ahead and declare a Y init as a double, and then inside the branch of our /1d interactively, we'll go through and we will simply have a printf statement that we would have otherwise, in our earlier example, also had in this location to please provide initial height and in feet per second. And once again, the prompts don't have to be identical to the sample. Basically, they just want to be instructive to the user. I'm more interested in making sure that the output matches. And so we'll have a scanf now with %lf. And we want to store it at the address of our Y init. Now, that covers the value that we want to capture from the user using scanf. However, when we make our function call here, we also need to have the additional variables that need to be updated for the function. Specifically, we need to have our variable for our T final, our Y final, and our VY final. We once again need to go ahead and declare these in our main. So we'll do our T final, our Y final, and our VY final. Hopefully the data type makes sense here. There's still going to be doubles. However, though, the big difference is that we are going to call the function and we are going to pass the address of these variables. And then lastly, we probably want to go ahead and also have a results variable, much like what we had inside of our function, so that now what we can do is we can say results are equal to Projectile 1D version 3. And we want to pass to it our y init. And now we want to pass to it the address of tfinal, the address of our y final, and the address of our vy final. Hopefully you can see now the difference between passing something by value, in this case the y init, versus by reference for the address of tfinal, the address of y final, and the address of, a little typo there, meant to say address of our vy final. And so the last three variables are all passed by reference or by address. They will be updated inside the function, which then allows for us to print the results in our main. And so at this point, what you can do is you can sort of borrow some from the output file that I provided, build your table. In this case, we'll have a printf for the column headers, as well as for the border. Once again, it just needs to match the output that I have provided for the given project. The length of the border and the spacing between the name and the value doesn't matter so much as long as you keep the correct units and the correct format spec. At this point, we're going to save ourselves just a little bit of time here, and that I know I'm going to reuse this again in our parametric. So I'm going to just copy it down. Now, inside here, we simply want to follow the output sample that I provided. There is our y init, feet, and we want to have our percent 8.4f to match the format spec, followed by a new line, and then the value, whatever it might be, for our y init. We do the same thing now with the additional values that we wish to display. There's our y final. Also with percent 8.4f. And you'll notice that we are once again back to just using the variable, not the address of the variable. Also note that I did have a little bit of a typo earlier. I said percent 8.4f and then accidentally forgot the f. Main thing is that you make sure and keep your output looking consistent. In this case, using percent 8.4f or whatever I have specified in the project. And then continuing on with this, you simply repeat this for each of the values in the table. We have our t init, which we have not specified a variable for. But what we can do is we can simply specify the format spec just as we did earlier, and then simply leave the value instead of a variable. Later on, you might decide that you want to add a variable and then provide some additional feedback from the user. We're going to do the same thing now with our tfinal. At this point, probably just becomes an exercise in copying and pasting and aligning things up correctly. And then we also want to do one for our vy final, which is going to be in feet per second. Following the same format spec. As well as for your vy init, which once again, we did not provide a variable for. And you'll simply want to hard code that value in for this particular example. Now, as far as the order in which you present these values, once again, it's up to a specific project. You could almost argue that you'd like to have the time first. You can simply shift that around inside the table. Now, at this point, then we might as well go ahead and test what we're doing. see if this works. So we'll go ahead and build it, make sure that we don't have any typos. That looks promising. We'll come out here to the command line. We'll go ahead and run our p4.exe/1d/interactive. Sure enough, I'm being provided for an initial height. And you'll see that the output, while the order doesn't necessarily match the sample file, the way that it's presented, in other words, the format spec, does. And we might as well go ahead at this point and repeat this process now for the parametric version. And you'll notice, though, that the difference is that I have to accept the arguments from the command line, just like I did in our P3. And so we will once again need to capture our y init. We're going to use the A to F function, and we're going to use our argv square brackets 3. If you're not comfortable with this, definitely go back and review the earlier videos. And then at this point, what you can discover is that you can copy then the entire table over. Now, earlier I copied the column names and the headers. I'm just going to comment this out for just a second. You'll actually see why when we get to the end of this project. Basically, a little bit of code reuse. You can just simply copy and paste those to the next branches in your if statement. But at this point, then the only thing you need to do is you want to make a call to your function, Projectile 1D version 3, passing to it once again our y init by val, the address of our t final, the address of your y final, and the address of your vy final. All right, let's go ahead and build it one more time. Let's go ahead and change our /i to /p and provide the additional argument from the command line. And you'll see that we get the exact same results. And just to prove that there's nothing strange going on here, we'll go ahead and change this value here to 200, just to verify that we are in fact getting different values in our table. Now, at this point, I just want to do one quick thing. I want to compare this once again back to our earlier version of our project. In this particular case, we want to take a look at the P3 that corresponds to the physics problem. And I just want to emphasize how this is functionally different. You'll notice that inside of the branch for the /1d in main, just like inside the /1d branch for the main in P3, we are collecting the information. However, the difference is in our P4, we are also printing the results after running the function, whereas in the P3 equivalent, we didn't have that luxury because we were not getting those updated values. Instead, all of that was handled inside of the function itself. And you'll notice here that I essentially have the equivalent table to what we just created here. The order is a little bit different, but fundamentally it's the same table. All of it is inside of the function. That was the only way that we could accomplish this. So hopefully this makes sense to you, as well as the difference between where we are declaring the variables. And so you'll notice here that in our 1D version 3, we declare less variables inside the function than we do in our 1D version 2. However, the big difference there is we have to declare those additional variables outside in the main. For instance, our t final, our y final, and our vy final, where we did in fact not have to do that in our P3. Now, the only downside that you've probably noticed is that we had to duplicate a little bit of code. And so in each of the branches of our 1D, unlike in the earlier version where we simply made a call to our Projectile 1D version 2, we have duplicate tables. Now you can handle this two ways. You can create another little helper function whose sole responsibility is to print out those values. Or in this particular example, we're just going to accept a little bit of redundancy in our code. Now, later on, we'll get around that redundancy as well. Now, what I encourage you to do at this point is to go ahead and pause the video. And I'm going to do the same thing. I'm actually going to go ahead and complete our /2D and our /beam. I'm going to leave that up to you to figure out how to translate essentially your P3 into your P4, taking the same steps that we did with our 1D. And so at this point, I encourage you to go ahead and pause the video, and I will see you very shortly. Welcome back. Hopefully you've gotten the functions completed now. We're going to go through the changes that I have made, make sure to explain hopefully to you how and why we're doing this again. You'll notice here that I'm looking at our Projectile 1D version 3. I've basically done a little bit of cleanup here, added some comments for the variables, the local variables that I've declared, some comments to myself about must initialize the local variables and so on. I've improved my comment block above the function itself. And then basically what I've done is I've just continued that theme on through the other functions. And so we'll take a look now at our Projectile 2D version 3. It's a little longer. It, of course, deals with the two-dimensional motion. You notice here that I have, particularly if you compare it to our P3, you'll notice that we have less variables to declare, primarily because we have passed more variables as arguments to our function. And so we have our v init and theta, which didn't change from our P3, but now we're passing the address of t final, the address of y final, the address of vy final, the address of x final, and then the address of vx final to accomplish then the calculations in 2 dimensions. I've declared the local variables that I need. I've initialized those local variables. I made the appropriate calculations for vx init and vy init, pointing this out for a reason you'll see in just a second. And then our calculations then for t final, x final, y final, vx final, and vy final. Notice that in all 5 of those cases, because these variables are passed by address, I have to use the indirection operator then to assign those values to the location then that I have passed. So remember, the indirection operator says I want to change the value at that location. And so once again, I've been careful. I've added extra parentheses just for clarity's sake here, where I'm dealing, for instance, with the indirection operator applied to the address of t final. Once again, that's not necessary. It just perhaps helps in reading the code a little bit better. Notice once again in our Projectile 2D version 3 that there is in fact no print statements other than this little helpful print statement up top that simply lets us know that the function's running. Once again, you can turn those off when you submit the project to your customer. It doesn't really matter. It just gives them a little confidence that it's actually doing something. We can continue on. We'll take a look at the simple supported beam. Once again, I've updated the comment block to reflect the function signature. I've also added a print statement at the top, as well as modifying or adding the results variable and then returning the results. Now, I think you would agree that the simple supported beam is probably the one that has seen the most profound change. As a matter of fact, the number of lines in this function dropped significantly. Other than our convenience variable of the results, we actually don't even declare a variable inside of this. This one's just simply strictly calculations. So hopefully you could sort of now see the difference between our V2, or the one that we saw in our P3, as opposed to the V3, which is in our P4. Now, going back to the main, you'll see that I've had to do a couple of things here. I've added a lot of variables, basically the ones that corresponded to the 2D and to the beam problems. I actually went through and added additional comments, not only specifying the units for each one of these, but also specifying where they are used, just to help us understand. And then I'm still leveraging the same if structure that we used earlier. You'll see here now, if we look at the calling 2D/I, basically I now have to prompt the user for two pieces of information, the initial velocity and the radians. Once again, I just simply got that from our P4 sample, roughly what I would like the input to look like to the, or excuse me, the output to the user to look like. And then I've built the table where, once again, I've done a little bit of hard coding for the values that we said were simply convenience. If they were important to us, then we would probably go ahead and pass them as arguments to the function. Those are later improvements that we can make to make this even more versatile. For right now, we're just simply going to hard code those values. You could create variables up in the top of your main and assign those initial values as well. But basically, I've just went through and for each one of my values then provided an output in the table after calling, of course, the function. And the function you'll notice here is a combination of variables by value, my v init and my theta, as well as the address or passing the address of the t final, the address of the y final, the address of the vy final, address of x final, and address of the x final. Now note one more thing with respect to the Projectile 2D version 3 that you did have to add if you were going to keep it consistent, an acceleration in the x direction as well as an acceleration in the y direction. But other than that, essentially, we've just moved the table out from the function into our main, which, as I mentioned earlier in the video, is problematic, or at least maybe inefficient at the very least, in that you now have two copies of the table. Once again, we'll resolve that in later videos, but for right now, just simply have this duplication of code between the /i branch and the /p branch and recognize that it is a place for some optimization later on. You'll notice also too here with the /p, much like in version P3 of this project, that we have used our A to F to capture the arg v square brackets 3 and assign it to the v init variable, as well as arg v square brackets 4 to our theta. We did not do any error checking. In other words, we needed to make sure that we actually got a valid value for v init and for theta. Again, that's outside of the scope of this P4, but just be aware of the fact that you need to start thinking along those lines. We did the same thing now with the beam, and the beam just has additional arguments for the /i. We basically want to enter in the load, the length of the beam, and the location of the load. And keep in mind that that is going to be the address of W, address of L, and address of A when we're passing it to the scanf. But notice now how with passing it to our function, the simply supported beam, we simply pass the variable itself, not the address of the variable. Part of the reason why is because the function does not need to change those values at this point. The only thing that they need to change, or the function rather needs to change, is going to be the value at the address of R1 and the value at the address of R2, which are the two reaction forces as a result of the loading on the beam. Once again, no additional error checking would be done. For instance, it would not make any sense to have a negative length beam or the load applied at some location off the beam. We'll want to handle those later on. You'll see here now we've accomplished the same thing by virtue of doing it parametrically by simply capturing the arguments from the command line. Now, let's go ahead and run a few examples of this just to make sure that this is working and that you understand then basically where the printing is being done. We'll start with our /2D since we went ahead and tested the /1D earlier. We'll do /2D interactive, put in the initial velocity of 100, theta as 0.7854, and you should have gotten the same table that you would have gotten in your P3 or the table that matches then the output sample, the P4 sample. And then we can do the same thing for our /p, and we have 100, and then 0.7854. And you'll see same table. Difference is, of course, that we're collecting the values from the command line and then using the A to F function to convert them into numeric values. Let's go ahead and test our /beam interactive. We're asked first for the loading on the beam, the length of the beam, and the location of the load. And in this case, it seems to be working correctly. R1 is 60, R2 is 40. And we can do the same thing now for the parametric version, which is going to be then just simply providing additional arguments here. And once again, we get the exact same output table. So we'll worry about testing the batch files and the input files in a separate video. But effectively, we are done with this project aside from needing to test some more scenarios. Hopefully you see now how we've essentially shifted the behavior or the responsibility of our functions so that in the P3 example or in the earlier examples, they were responsible for printing the output. Now the functions themselves are no longer responsible for printing the output. Optionally, they could, but we instead want to focus on printing the results in the main, which brings me to one last comment on each one of these functions when it comes to responsibility. And what we'll do is we'll focus back on our projectile 1D version 3. And specifically what I want to do is I want to focus on whose responsibility it is to initialize our T final, our Y final, and our VY final. If you'll notice, I did not initialize any of our arguments. You could make a strong case that this was very weak programming. And instead, we could make the argument that we would need to initialize these values inside of the function. Well, once again, there's two schools of thought here. The purpose of the results variable is to tell whether or not the function ran successfully. In other words, should it have made any changes on any of the variables if it failed? And once again, there is no right answer here. It just depends on the behavior that we would want to have. In other words, would we by default go ahead and initialize our T final, our Y final, and our VY final, recognizing that we may overwrite whatever value was in them? Now, in this particular example, we're only running these functions once, so the answer is probably no. And so what we want to do as a last piece to this project is in addition, to initializing our results, we probably should take just a second and go through and initialize each one of our variables that we have declared in main. And so we'll start off with our Y init, our T final, our X final, our Y final, and so on. And so let's just take just a second to sort of close the loop here. In other words, make sure that we don't accidentally print out nonsense values, especially in lieu of the fact that we are doing no error checking. And so there's our theta. I'm going to go ahead and do our VX final equal to 0, our VY final equal to 0, W, L, A, R1, and R2. Just make sure that you haven't missed any. Fundamentally, just make sure to initialize all of your values in main. We will once again revisit this topic later on and decide whether it's the responsibility of the calling functions to go ahead and reinitialize those values. So once again, if you have any questions, comments, or concerns, don't hesitate to reach out to me. Hopefully you found this video useful. And as always, thank you for watching.